Our next lesson in the Bonding and Intermolecular Forces unit is on the valence shell electron pair repulsion theory, or also known as the VSEPR theory, as you can see abbreviated here. The learning target that we'll start working on here is learning target number 3 in our essential standard for this unit here. We want to be able to use this theory to determine the molecular shape of molecules. Now this particular video will not look at really any particular shapes, just the theory behind how we will then use to determine what those shapes are. So what is the valence shell electron pair repulsion theory, or again known as the VSEPR theory, or some people might say VSEPR theory even though the S comes before the E. So what the theory tells us is that electrons in a molecule will spread out as much as possible in order to reduce the amount of repulsion that occurs between the electrons. Because recall, all of these electrons, whether we're talking about electrons that are being shared between atoms or lone pair electrons, they're all negatively charged. They're going to repel each other, and so this theory tells us that these electron groups are going to spread out as far as they possibly can to reduce the amount of repulsion between those electrons. It is this idea then that determines the actual shape that the molecules will take. Let's consider an example for aluminum hydride. If you were to draw a Lewis structure for aluminum hydride, you may well draw it like you see drawn here, where you have the aluminum as a central atom and then the 3 hydrogens bonded to it, with the aluminum sharing 1 pair between each of those hydrogens. But the question we're trying to get at here is, what does this molecule actually look like? If we were to be able to take a picture of a molecule, would it look like this? Would it have this T shape to it? And the answer to that's actually no. The valence shell electron pair repulsion theory tells us that these groups of electrons around the aluminum, there are 3 groups. Okay, there's one group for each bond there, so I have a group here, a group here, a group here. They'll spread themselves out as far as they can around that central atom. Well, if you think about what that would look like, it would look something like this, where we get more of a triangular shape, where we don't have this T shape. And there's kind of 2 pictures of it here. We have this, the one on the very bottom here, the small view of it. You can see that it actually all lies flat on a plane. It lies flat to the table there. And then if we hold it more upright, we can see it here where we have this triangular shaped molecule. We would actually call this trigonal planar. Now the point of this video is not to know that geometry name, trigonal planar. The point is just to start thinking about how are these electron groups actually going to arrange themselves in order to get as far apart from each other as possible. You'll notice if we would arrange them like we draw the Lewis diagram here, and there's nothing wrong with this Lewis structure here. You can draw it just like this if you would like. The problem is this doesn't actually show us the shape. If this were the actual shape, these electron groups here between the top hydrogen and then the 2 hydrogens on the right would just be closer together than what they really needed to be. And likewise, these here between the 2 on the side would be farther apart than what they should be. So what about if we had lone pair electrons? So what about lone pair electrons on the central atom? Are they going to affect the geometry? The answer is absolutely yes. Let's consider this. If I ask you to draw a Lewis structure for water, you very well may draw it just like you see here with the oxygen in the middle, because that will be the central atom. And then you'll have 1 bond to each hydrogen, and then you'll have 2 lone pairs on the oxygen. And that would be a perfectly legitimate Lewis structure for water. However, it doesn't actually communicate what the geometry, the shape of that molecule is. So I want you to ask yourself, these 2 lone pairs on the central oxygen, they have to also be considered. So we have 4 total groups of electrons. When we say groups of electrons, each lone pair is a group, so that's 2 groups of electrons, and then each bond is also a group. So there's 2 more pairs, so that's 4 total groups of electrons. How would I take 4 groups of electrons and arrange them around that central oxygen so they can get as far apart as possible? Go and pause the video and think about that for a second. Alright, my guess is in your mind you might have envisioned some sort of square where each group, kind of like we have this drawn here, where maybe the 2 bonding pairs go out to each side and then the one lone pair goes up, 1 lone pair goes down. And you might think, well, that would be the farthest apart they could possibly get. The problem is there we're only thinking in 2 dimensions. Remember, this is a 3-dimensional structure. We can put these 4 groups across those 3 dimensions. So arranging these 4 groups would look something more like this, where we have kind of a pyramid type structure. This puts each of those 4 groups of electrons farther apart from each other than if we just did some sort of square type shape, if that's what you were thinking. So the point of this, again, is not to become real familiar with the actual molecules and their shapes. That we'll work on in class as we start our molecular geometries activity in class tomorrow. But what the idea is, we do want to start thinking about in 3 dimensions. How can I arrange these things to get them as far apart as possible? Now you might still be wondering how this picture here applies to water, because what I'm kind of showing here is a central atom with 4 atoms attached to it. Well, just picture 2 of these atoms, 2 of these red atoms here, as being the lone pairs of electrons. Or another way to look at it, I have another picture here, would be something more like this, where you can see we have this same tetrahedral structure. That's actually what we call this geometry, where we kind of have 4 points to a pyramid, if you will. We call this tetrahedral. And 2 of those points would be hydrogen atoms. The other 2 points would be those lone pairs of electrons that you see there. And so this is how we get this geometry for water. Alright, the last thing to consider here is how does the repulsion between bonding pairs compare to the lone pairs? In other words, if I have 2 bonding pairs of electrons, will that be the same repulsion as between a bonding pair and a lone pair, or between 2 lone pairs? The answer is all those combinations differ. There are ultimately 3 different combinations. We have the repulsion between 2 bonding pairs, so bonding repulsion. We have the repulsion between a bonding pair and a lone pair. Okay, then that would be in the middle. And then the greatest repulsion is between lone pair, where those electrons are going to spread out just a little more because of that increased repulsion. So the least amount of repulsion we have is whenever we have a bonding pair repelling a bonding pair. Another way to look at this, I'll just pull up that same picture we had from the previous slide. Water is an example of all 3 of these situations. We have repulsion here between this pair of electrons and this pair of electrons with the hydrogen bonds there to the oxygen. That would be the least amount of repulsion in that molecule. The second would be between a bonding pair and a lone pair. So between this shared pair of electrons here, between the oxygen and the hydrogen, and this lone pair, that would be a moderate amount of repulsion as far as the VSEPR theory is concerned. And then the most repulsion would be between these 2 pairs of electrons, these 2 lone pairs, because they're going to spread out more, because they're not attracted to another atom at the other end down here like these pairs are, because they're shared between two different atoms. So these are all ideas that we will consider as we start learning about these molecules and how we build them and how we define their shapes, and what we call the bond angle, which you can kind of see here written for the water. This happens to be 104.5, or right about 104.5 degrees. We'll be learning all about that as we start building these things. Okay, so this video here, we've looked at how we start to determine the molecular shape of molecules. Our class activity, once we start doing this, we'll get at actually building these molecules and looking at what we call them, so we have a way of having some sort of terminology for understanding the shapes of molecules.